So what you are doing? Okay. So we were discussing integration. So we defined integration. So what did we do? Suppose suppose it's writing. Suppose if we have a f, so we denoted by s plus simple functions. So suppose s plus is a simple function on x. So maybe I will start with the s plus x, all simple functions. Then for f in s plus x with f equal to summation lambda I 1 n. So we defined integral f over x du equal to summation lambda I. Okay. And we verified that this is well defined. It does not depend on the partition, and it is linear. Okay. It's linear means integral af plus dg du equal to integral it's integral b g du for all fg s plus and ab. Okay, so that's what we have verified. So now our aim is to define integration for any positive measurable function. So by forgot, this is all simple function, not all simple functions, all positive simple functions. Possibly it can take the value infinity, all extended real value simple functions. Okay. So now we want to. So now we also know. We know for all for given. I mean, f which is positive, if a positive there exists fn real value. I mean, this need not. I mean, this will not take the value infinity. Real value simple functions. Real value positive value. Simple functions such that fn increases to f. So we want to define our integral as the limit of. I mean, we want to define integral f du as supremum of integral f and du. So that's what we want to define. Okay. So to do that, we need to verify that it is well defined. Okay. So before doing that, we will first verify that the what do we want to verify? We want to verify that this. I mean, suppose some simple function, sequence of simple functions increases to another simple function, then the integral also increase. Integral also increases with the corresponding value. So for that, we need the following lemma. I mean, this is the lemma we want to. Whatever I said, this is the that's being written in. This is the lemma. So suppose Fn a sequence simple functions and f is another simple function such that Fn increases to f. Okay, then integral Fn, supremum of integral Fn equal to integral f. So this is what we want to see. We want to define our integral, we want to define integral for any measurable function as the limit of some integral of simple function. So before that, suppose some simple function increases to another simple function, then we want to say that the corresponding the value of the integral also increases to the corresponding value of the integral. So before this, there is another lemma. Maybe this is just a remark. If fg or in S plus and f is less than or equal to g, that is f of x is less than or equal to g of x for all x in x. Okay. Then integral f d mu is less than or equal to integral gt. The proof is, it's a follows. So since this follows, since if f is greater than or equal to 0, implies integral f is d mu is greater than 0. So if f minus g is greater than 0, then integral f and linearity. F is greater than g, then f minus g is greater than or equal to 0. Then integral f minus g is greater than or equal to 0. Because integral is linear, integral f is greater than integral g. So I think this is clear. Okay. So if f is less than or equal to g, then the integral f is less than or equal to integral g. So we want to use that for the proof of the lemma. So proof of lemma. So we have simple functions fn, which increases to another simple function f. Okay. Then all, so since fn increases to f, okay, so that means f is greater than all fn. Integral f d mu is greater than or equal to integral fn d mu for all n. So hence then it's true for the supremum also. Supremum and integral fn d mu. Okay. So one way is proved. We have to prove the other way only. Okay. So need to prove integral f d mu is less than or equal to integral fn d mu. Okay. Supremum. So we need to prove the other way.
Sir, can you show the lemma once?
Lemma 1. The lemma says that if we have a sequence of simple functions fn and another function f such that fn increases to f of x. It just means for each value f1 x increases to f of x. Maybe I will write this again clearly. Fn x increases to f of x. So this is just number, okay, for all x and x. That's what we mean. We will write without x if this happens for all x. Okay, you will say fn increases to f, or when this happens for all x. Okay, is clear?
Yes, sir. Thanks.
Then the integral also increases. That's what this says. The integral, that's what it says. The supremum of the integral, supremum of integral fn equal to f d. Okay? So that's what we are going to do. One way is clear because the integral preserves monotonicity for positive. If f is greater than g, then the integral f is when you have two positive functions, then f of x is less than or equal to g of x, then the integral preserves the partial order. Okay. Okay. So because of that, we have proved one way. Okay, integral f d mu is greater than or equal to integral f and d mu. We want to prove the other way. Okay. Okay. So to prove this, we claim the following. There is the following claim we want to use. Suppose we have another simple function. Suppose h is a simple function. Okay. Incidentally, I will define now. So just a digression. I mean, I defined integral over whole set x. We can define integral over any set. So define integral of some function f, some simple function f d mu over some set e equal to integral of 1 e f d mu. Plus e should be a measurable set, of course. E is a okay, you just multiply by the indicator function or the characteristic function, the function f, then that's what it means by you integrate over the set e. I mean, this function is 0 on e complement. So whatever you integrate there, you will get the value 0. So that's what this means. Okay. Now this is the so we want to prove the lemma. Before proving that lemma, we have a sublemma. Suppose h is in some s plus. I mean, this is true for general measurable function when we define the integral for all measurable function. But for the time being, it's in a s plus mu of e equal to integral over e h d is a measure. So if we have a simple function h, then you define mu of e equal to integral over e h d mu, then mu is a measure. Okay. So this is clearly, I mean, if you have e is an empty set, it's 0. So we only have to verify countable additivity. So suppose En contained in and En intersection equal to empty. Suppose if you have a disjoint family, then we want to verify the countable additivity for the nu. Then nu will be a measure. That's what we want to do. So then we want to verify the following: nu of this En. We want to verify that we can take it out as sum. Take out the disjoint union as summation. So that is equal to, so that is integral over this. So this is equal to, maybe I will write it like this: 1, this En of h d. So, okay, h is just a simple function. So let h equal to summation. So that is over n, I equal to 1 to m lambda I 1 a. So suppose h is a simple function, so it will look like this. Okay, then mu of s equal to, so I just rewrite this 1. So this is just arbitrary multiplication. So summation 1. I mean, I can just take this out. Okay, so because the integral is linear, so I'm just following one step. So we'll have lambda I 1 a I. Okay, so this is equal to summation I equal to 1 to n integral over x lambda I 1. So if you multiply two indicator function 1a times 1b, that is just going to be 1a intersection b. Indicator function takes the value 1 in that set and 0 outside. So if it will take 1 in the set A, 0 in the A complement, 1 in the set B, 1 in the 0 in the B complement. So if you multiply 1A times 1B, it is just 1A intersection. Okay. So this is just going to be AI intersection this joint union. So this is going to be, this is N. Then that's, I mean, then we know what is that integral is, which is just going to be lambda I times mu of AI intersection disjoint union of n equal to 1 to infinity. And since mu is a measure, lambda I summation n equal to 1 to infinity. This is disjoint, and I mean, you can take AI inside, and which is just mu of AI intersection. Okay. And then you can, I mean, this is just a finite sum, and you can bring this sum here, and you can take the sum inside. So I will not write all those steps. So this is equal to n equal to 1 to infinity summation I equal to 1 to, this is m, okay, lambda I mu of AI intersection A, okay, which is summation n equal to 1 to infinity. So this you can just write it as integral of lambda I summation, you can take it summation also inside, I equal to 1 to lambda I indicator of AI intersection AN, which you can write it as 1 AI. I think this is clear. So 1 AI. Okay. So this is summation n equal to 1 to infinity. That is just our h summation. That is just h integral of h on En. Okay. So nu is a measure. So what we have just proved is, if we have any simple function h, and if you have any simple function h, and if you define nu of e as the integral h d mu e, then that nu is a measure. Okay, so it will satisfy other properties. It's there is a, if some En increases to E, then nu of En will increases to that. We want to use that property. For that, we have verified this is a measure. But our aim is to prove this. Our aim is to prove that, what is our aim? Our aim is to prove this lemma. This lemma says that if we have a sequence of simple functions Fn, which increases to some other simple function F, then the supremum also, the integral also increases to the corresponding thing. That's what we want to do. For that, we have proved one way. We want to prove the other way. So to prove the other way, it is enough to prove the following. So now back come. So this lemma is proved. Okay? So this is what sublemma is proved. So we have proved the sublemma. Now coming back to lemma, original lemma, which is if Fn increases to F, then the integral Fn increases to integral F. We need to prove the other way. It is enough to prove what? For all, let me write it. For all C in this interval 0, 1, okay, for all C in this 0, 1, integral, I think C times is the integral Fn. Then we can take the supremum over C and okay, is enough to prove this, right? Okay. So it's enough to prove this, no? If this is true for all C in 0, 1, then this is true. You can remove the C. If this is true for all C, then you can take the supremum over C and you can prove. It's enough to prove this, right?
Sir, how do we get n here in this? What is this n?
This n. The n here.
Yeah, right hand side of the last equation.
No, I didn't understand. We have, in our original thing, we have Fn increases to F, no? We want,
yes.
We want to prove integral Fn increases to integral F. We have already proved that integral F is this is greater than this. Okay? This is greater than this. We have proved.
My question is, are you asserting here that like for each C we can get an n such that
No.
equation?
No. I'm saying this is for all. Okay. So your question is that. So what is that? So yeah, good question. Great. Yeah. No, we have to prove the supremum. Yeah, it's enough to prove the supremum. What do we have to prove?
So it should be C times integral F less than equal to supremum of the integral of F and mu, right?
C times integral F is supremum.
Less than equal to supremum.
We have to get the supremum. Yeah. Yes, that's right. Yeah. Right. This is what we want. It's enough to prove this. Right?
Yes.
Yeah. So this is what we want. So for that, we define the following. We define the following set. En equal to all those x in x such that Fn x is greater than or equal to C of. So this depends on n, right? So C of x. Okay. This is just we collect all the x which satisfies this. Okay. So now since Fn increases to F, okay, and this is Fn x increases to F of x. Each x after some time, given when you fix a C, I mean, when you fix C, I mean, we want to prove this whatever this star. We want to prove this star for all C. So we fix an arbitrary C. Okay, we fix an arbitrary C, and we define En to be like this. Okay. Now, since fnx increases to f of x, for every x, so there will be, I mean, for every x, after some time, the x will be in one of these En. I mean, every x will be eventually in one of these En, right? That's right.
Yes.
After some time, this x will be in En, and I mean, it will be after. I mean, eventually, after, it will be all those En after that. So that just means one En. That just means En increases to this. En as a set increases to the whole of x. So this implies one En as function increases to the function 1, constant function 1, right? 1x or something, 1x, I mean 1x or whatever, which is the constant function x, right? So now we define the following. Now the integral C f g mu, okay, that's what we want to consider, over x. Okay. So which we can write it as so now this CF is a I mean we have the sublemma, no? Where if we have any integrable, any simple function, then you can define a new measure like this, and I mean new function, set function like this, which is a measure. Because of that, I mean, since 1En increases to that, this is equal to this is you can multiply by 1En and CF this limit of supremum. I mean, supremum is same as the limit, so limit, right? This is C. Okay, you can just, I mean, this is because this satisfies the measure property. I mean, take H equal to CF. Okay. Then nu of E equal to integral H d mu E is a measure. So because 1En, so nu of En will increase to, because 1En goes to 1x, or that is not needed. Okay, this is not needed. En increases to that. En increases to nu of x. Okay. So because of this, and so the sublemma, whatever the sublemma we approved, because of this is true. Okay. So this is just limit n going to infinity 1En CFX. So which is okay. So now see, notice, maybe I'll write this. Notice what you have. The En is defined like this. Okay. So 1En. So in En, this is satisfied. 1En fnx is greater than or equal to C of 1En f of x. In general, there may not be in general, there may not be any relationship between Fn and f of x. I mean, it is just f of x is greater than Fn. this relation may not be satisfied. But when you multiply by 1 en, we have in the set 1 en, this relation is satisfied, greater than or equal to Cf of x. So if you multiply by 1 en, this is true, right? Cf of x. Okay. Okay. So as functions, you can write like this. So this implies this thing. This is equal to integral. So you have 1 en. So integral. So this is less than or equal to 1 en. Fn. Fn. And you can remove that 1 en. I mean, because there is just integral Fn, right? Or you can write lim in for something. You can write like this. Is this okay?
Yes, yes. It's fine.
So this, I mean, this is just the suprema. When this increases, so that is just the that limit is same as the limit anyway, which is the supremum anyway. So this, since this is true for all C, I mean, we have, that's what we have already noticed. Since this is true for all C, so what is that integral? Since this is true for, I mean, then you get integral f du is less than or equal to limit of integral f. Okay.
So, but why did you write liminf in that state in that line? Like, what is the use of liminf here?
No, no. Well, I should have written remain there. I think earlier also see, you have something less than something, but sometimes the limit may not exist. So you better write limit kind of thing. That's all. Here the limit is existing. So in general, if you have some limit and something is less than something, then this is less than or equal to. It's better to write limit. I mean, that's the right thing to write.
Okay, okay.
If limit exists, it's fine. But here its limit is existing, so it's
Okay.
so. But the time is 5:59. So maybe I will stop here today. I'll continue next Thursday. So okay, I will try to post the notes tomorrow or sometime. Okay, in the Moodle. I think it's possible, so I will try to post it. Okay. Okay, we'll end the session.
Sir,
Yeah.
sir, can I talk with you a bit later after the class?
Here itself. Okay.
Yeah, maybe.
Okay. So you want to enter after some time, or you want to wait for everyone to go?
I am fine with either.
15 minutes, after 15 minutes, you come back here.
Okay, sir.
Yeah, I will be here.